I go to the gym now and work out there exercise, right? Then be hilarious.
Good morning. Sure. No problem. Appreciate that. And they have the link, right? This leads link. Oh, thank you. Okay. Okay. Thank you. Bye. I check with that. Students, I think you guys hear me. Hello, students. Can one of you unmute and speak, please? Let me know, guys, when I can start. Can one of you unmute?
Yeah,
I know Vishnu is not there, but the professor said Shweta or Smita would be logging in. Shweta or Smita, can you unmute and speak? Guys, can one of you unmute and let me know if we can start? Guys, when can we start? Should we wait for some more student? I'm gonna ask one of you to unmute. Let me pick the name. Okay, and what name is Soumya or Jyoti or Mallu Hari? Can one of you guys go on mute and speak? Sheikh or Hafiz, can one of you guys unmute and say whether we can start the session? Sheikh? Guys, please tell me whether we can start this. All right, check with them. Thank you. Let me know, check with them. When you guys are ready, let me know so that I can start the session. All right, guys. Good morning, ladies and gentlemen. So, trust you guys had a very good last 2 weeks, the festivals and the internal results. All that. So, this week we are going to understand SVM, which is support vector machines. Just a second. Yeah, support vector machines, which are essentially, or which is essentially an algorithm in identifying categories of classes, and the associated project of how we can apply that in real life or real world. However, before I begin on this topic, algorithm as well as a project, I also wanted to draw your attention to the fact that we have skipped or we have cancelled last week's sessions due to the festival, etc., as requested by Professor Suraj. And I'm doing that session today, which means we are running at least 1 week late, right? So that is one point. 1 week late with respect to the overall schedule, which was published and website. Nonetheless, I have updated the first course kind of FC as of till today, and I have published that under the announcement. FC. We will obviously have to tweak it around based on Professor Suraj's inputs and obviously Dr. Pravin San's inputs. So that's it. That's that. And also one more important point is that the submission date going forward, as I mentioned in my previous session, would be the next Thursday. So session is on Saturday, Sunday this week. The submission of the project would be next week Thursday. So that's the point that I'm taking into account since last 2 weeks. But these are the 2 points. Let's start with the session. So this week's session, I just wanted to bring in some color in terms of knowledge color, which is essentially the time of the year where the Nobel Prizes are awarded to those whose work in the field of education, field of industry, field of study, research, academia is recognized globally. So we'll start with that, because that has some real significance for all of us to see where we are today, the crossroads of the technology, particularly if we are a technical. Disclaimer. And that. So let me also spend a couple of. We'll come back to the agenda. So one key point that I wanted to highlight to all of you guys is that just a second. So this year's Nobel Prizes actually is a very important thing for all of us, and particularly all of you to take a note of. Why? Because artificial intelligence and related work across the spectrum of streams of studies or research has stolen the spotlight, be it physics, be it chemistry, and be it, there's one more, biology or protein study, human protein study. Those people who have either worked and invented or created, discovered some of the tools and techniques of artificial intelligence and machine learning, or those that have applied those techniques have been recognized by their work in the AI, and leveraging the AI have been recognized with the examples of, as you can see, this gentleman here, you would probably read him, study a lot about him if you are a true AI engineer. Jeffrey Hinton, I think British born, but American/Canadian. I think he teaches now in the University of Toronto. He worked for Google for quite a long time. This is a gentleman who essentially invented the mathematical or artificial neuron, which we studied in our first session, inaugural session. And some of the techniques that are the methods that is invented in the neural networks have been recognized, and he's been conferred along with John Hopfield, the other gentleman who's the AI scientist, who has invented essentially Boltzmann network, etc. Right? These guys have used the physics fundamentals to arrive at the machine learning techniques that they have unveiled or created or invented. The other three gentlemen, these are related to the chemistry. The first one, I think Baker has used the machine learning techniques in creating or in designing a computational protein for the purposes of studies and research. The other two, Demis Hassabis and then John Jampa, all these two guys were part of Google DeepMind. DeepMind was a UK company which was acquired by Google. These guys are essentially responsible for many AI ML tensors that you might have used for inventing all of these and creating. In fact, Hinton as well worked for DeepMind. He's got lots of his a contribution on the GPTs, the pre-trained transformers, right? And even the transformers themselves, of course. Attention's only need is Vaswani and other traits, but thinking obviously was getting research. So the key point that I wanted to draw your attention to is AI and ML are pervasively, and Alfred Nobel Institute chose to recognize the impact AI and ML is making and bringing into the human society towards the positive things, of course, and also become destructive, just like Alfred Nobel's atom bomb. It's the power that gets utilized for benign purposes or malicious purposes, right? So, if you have any doubt in your mind whether I have chosen the right field, I think you should completely remove that mind, because AI is the happiness, right? Having said that, this is a little visuals that the Nobel announcement used, particularly for Jeffrey Hinton and John Hopkins' work. John Hopkins essentially Boltzmann machine, various network machines, Hopkins network mechanism, hypothesized. And this is essentially our neuron structure, right? And these are the weights, and we talked about weights and synapses, right? If If the weight is stronger, then the synapse, the current that flows to the next cell is higher, which means that weight value is higher in terms of mathematical value. If it is weak, that may go, may not go, that may trigger, that may not trigger, or its contribution in triggering, its enough value triggering the next neuron would be or relatively less, right? And the other thing is the memory, how the memory is stored, what is essentially memory, how the learning gets in there. These are little advanced subjects, but it would be good to go through these. This will give you an immense understanding, which would be helpful for you to build the best career. All right? And said that, let's get started with SVM. So support vector machine is a classification algorithm. Let's start with the basics. What is classification? Right? So all of you are familiar with Google Mail. Right? When you use Google Mail, you would see most of the times there is a junk folder, and then there are other folders. So what goes into junk is considered as spam, and what goes outside the junk folder, the emails, are considered non-spam or spam. So an email that comes into your inbox, or which is being delivered to your address, email address, gets classified into one of the two, either a genuine or a spam. And who does that? And when it is done automatically by Google Mail server, Gmail server, and it happens as it comes in, as the mail comes in. So we are classifying received email for the efficiency purposes of the reader, so that it doesn't waste time and this inbox does not get spammed, we call it, jammed, right? Into genuine or not genuine, based on certain learning algorithm, which we call it as a classification, spam classification. So essentially, classification is the process of assigning data into one of the classes. These classes could be spam, genuine, two classes, or binary classification, or it could be more than binary, which is multinomial classification, right? And this is an algorithm where, based on the trained weights and the trained algorithm, when a new unseen data comes in, that can be classified into one of these two or one of the main, multinomial or binary classification. Right. If you see here on this picture, on the slide that I have, this is actually I have created this image with the help of ChatGPT. I have a paid subscription for ChatGPT to create images for the classification. And as you can see, the red squares and then the circles, the dimensional. You can see that they seem to be having some sort of classified area, right? Some irregular, not a straight line type of shape. Of course, there are a couple of, unexpected in that category, in that area, blue colors. But if you look at net on an average basis, you can see two non-linear, irregular grooves, blue and red. So this area that I just drew here, this red color that I'm drawing, is a boundary of these classes, also called decision boundary, because if a circle or a square, if it lies towards this side of the boundary, then we call it is belonging to blue color category. You can assign some attributes and values, 0 or 1. And if these shapes or data points falls onto the left of the boundary, we call it other class, red class, blue class, red class, right? So essentially, support vector machine is a classification algorithm. And it learns to create such boundaries based on the decision boundaries based on the training data. Any other classification algorithm essentially creates a model that would honor or that would create this boundary, mathematical representation of this boundary, so that it uses, it creates a formula to arrive at a value which can be recognized whether this value lies to the right side or left side of the decision boundary in case of binary classification. Right? The goal of any classification is to create a mathematical form to identify or to formalize a decision boundary. That I'm trying. And where can we use? Where do we use such model in our real world, real life? One we talked about it just now, right? Identifying an image as either a spam or a genuine, or if you use a credit card, marking a credit card in your statement or immediately after the transaction, whether it is a genuine transaction or somebody has stolen your data and then you essentially continue fraud. This is possible based on certain parameters, regular habit of where do you spend. Where are you currently? When was your last transaction? And if the current transaction, let's say last transaction occurred in Bangalore 1 hour ago, and the next 1 hour, your next transaction occurs in, say, Miami, Florida, or Las Vegas in the US, and there is a suspicion, right? But obviously, it's not even possible to be in these two locations within a time span of 1 hour. Yes. So there are certain parameters that can be learned, like this. So a classification can be used in validating or attributing a particular credit card transaction as a genuine or or even most importantly in today's, what should I say, today's explosive world of e-commerce, quick commerce, right? What are all the customer categories? Whether he buys only certain products, or she buys only certain products of certain cost, or certain products of certain type, luxury, staple groceries. Various such categories a customer can be categorized, which would help marketing of a business to target when there is a new launch of a product, a different product belonging to that particular category, or when you slash the prices to improve the sales or increase the sales. So that is a classification to do. Let me have some water. Any questions? There is the document so far. Remember, there's no dumb question. Also, brace yourselves. Today's session probably has the highest mathematical content, which is highly complex, because I'm touching upon in detail on the convex optimization, which is a fundamental concept that you as an AI or ML or computer engineer should have the basic foundational blocks clearly understood. So brace yourselves for lots of mathematics in this session, right? So while I address few use cases of classification in real world, let's quickly glance through some more specifically based on the business decision-making use case. So in making a decision in predicting, for example, in healthcare, in fact, project is going to be based on this case. Is based on the diagnostic data. The diagnostic data could be, let's say, an imagery like X-ray or computer chromatography, CT scan, or it could be even a sonogram, right? UV scan. Or it could be a simple complete blood culture with some values. How many red cells, how many white cells, etc. etc. A value, a continuous value, right? Or the discrete values, whether it is higher than this, lower than this. Based on this, predicting a disease, whether a person has a disease or not. For our project, we would be actually trying to predict the breast cancer based on around 400 sample data that was published by University of Wisconsin. This is one of the classical data set, and then the project that any machine learning engineer would have to get familiar with. So instead of trying out something from India, I chose to use this data set. In fact, IITs of our country use this as a classic example. Classification. Right? Other things in automating the tasks. Also, we talked about which one? Email classification, whether it is a spam email or genuine email. Right? Uri Venkat, you will have your camera on. You may want to switch off the camera so that we can conserve that. So, automatically classifying a particular mail in spam or not spam. There are many such automated scenarios that businesses need so that they can avoid human intervention and bring the efficiency. And also understanding the fact that, for example, we talked about the customer categories. Similar, right? Categorizing customers, putting them, boxing them into various categories so that you can targeted marketing campaigns to get more bang for your marketing buck in terms of the revenue or in terms of the profit. Right? Also improve decision making, particularly, you might be familiar with it. When you go for a house loan or a vehicle loan, there's a lot of process that you need to go through and submit lots of documents, etc., which will enable, based on that data, a bank to arrive at, to classify you whether is there any change that you would default, meaning you would not pay the loan. Right? Essentially, across the globe, banks use the software for this classification based on the historical data of the person, as well as the collected data during the application. So, classification is used as well. Knowing a person, whether he or she is going to default, is critical for particularly businesses like banks, particularly that are into loans. Right? If the bank knows that the person is going to highly likely in defaulting, then they can avoid loan becoming a non-performing asset. That's a technical term for a loan that has gone default or the borrower has not paid or will not pay. Right? Also, handling complex data, particularly data with lots of features, dimensions. Right? One biggest example that should come to your mind is any computer vision or facial recognition, face or whatever it is, where there is a visual data always has lots of information than textual data. And also audio data always has lots of data points, right, or dimensions. So identifying faces, such as Windows 10, Windows 11, have your face recognition for your login. It's called Hello World, right? Based on the imagery, based on infrared camera, or based on the photo data itself, you can arrive at a pattern unique to each user, which can be used to decide whether this is this person or not. And some of you might have seen many of the movies, particularly of interest is, Tom Cruise movies, which use this heavily. One of those Mission Impossible and Ghost Protocol or something, where a person's gait is analyzed in Morocco to get some sort of secret card, ID card. Right? All these they are not imaginary. They actually do happen, and they do actually use that classification algorithm like a sphere that we don't be talking, right? And of course, the natural language processing, now NLP is the fundamental fabric of any GPT, particularly ChatGPT, in predicting or in generating the text or audio or video, right? Because you have to predict the next information element. Could be text, could be audio, could be video frame, right? Where, the written text can be used to analyze the sentiment, the mood, the tone of the person, and persona or character, and some attributes of that person. In fact, there is an ancient, not so ancient, there is a pretty much maybe decades or centuries old science of study called graphology. Graphology is based on graph, what you write, based on how you write, how the character you write in English, or in any other language, how stressed it is, how big it is, how narrow it is, how small it is. People can identify your character. In fact, it is used in some of the criminal investigations as well by forensics of the police department, right? So sentiment analysis is something similar, but it tries to take the semantic sense of the text that you've written and it's a semantic meaning, right? So classification algorithm, those are the use cases of the classification algorithm. But let's try to understand a little more deep into the classification algorithms. So classification algorithms, potentially you can divide into various categories based on the attribute you look at, right? If you look at the outcomes of the classification, where outcomes could be 2 or more than 2, then you call them as binary classifier, right? So we talked about it already. Outcomes are always 2. One example we have seen already in our second session or third session, logistic regression, where we classified the data point as belonging to one of the 2 classes. Simple naive Bayes as well, we would be naive Bayes. We would be also looking at the project of classifying an email into spam or not spam. Again, this is also binary classifier. Multinomial classifier is essentially where the outcomes are more than 2. If time permits, we'll be looking at those k-nearest neighbor, DCT, decision tree classifiers, and naive Bayes but non-linear. Right? Linear is one of these 2 distinct variables. And of course, you should also know softmax function, which essentially leads to probability of category. Multinomial logistic regression, this is also softmax also. These are the multinomial classifiers. And the other attribute, which is based on the data characteristic, whether the data is plain, simple, linear, you can use a straight line and then divide them into this or that, then it's linear, so linear classifiers, or it is not so linear, it's a zigzag, it's boundary classification, then it's a non-linear classifier. Right? Obviously, linear classifiers have the data which is linearly separable. That means the boundary is represented using any linear transformation, linear function, linear equation. So what is linear equation? Anyone? A1 plus x1, A2 plus x2, x1, x2 are dimensions or features. This is a linear equation. So the boundary line can be represented using this when it's linear classifier. But instead of x1, if you use, let's say, a1 x1 squared, a2 x1 x2, blah 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 da 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 da. So you have the order of this equation is 2. It is not linear, it's non-linear. So if the data is distributed non-linearly, then you would have to use non-linear boundary, hence they are called non-linear classifiers, and usually it happens with a complex data. Essentially, pattern is complex, right? Some of the examples we just saw already a while ago. Logistic regression is simplified classification. IEA based support vector machines can be used for both nonlinear and as well as linear classification. LDA, linear discriminant analysis, also called the Gaussian discriminant analysis. Essentially, it is for the data that is distributed in a Gaussian model. Gaussian is nothing but the bell curve, right? Normal distribution. Decision tree classifiers based on which are nearest, all the nearest neighbor. Just like our colonies in our Karnool, NRPate is a colony, right? Budwarpate. So if they are all nearby and having a similar characteristics, so they are like colonies or nearest neighbors. And KSM, we have around 150 to 300 such colonies in Karnool, right? In the Karnool. Similar mechanism. Random forest is not be talking about it, but this is for your FYI. Right? Neural networks also can be used to classify it. So let's try to look at the characteristics a little more detail of linear and nonlinear. Though I have already mentioned a little while ago, but let's understand visually. Like I said, in a linear classification or linear classifier would have a linear boundary which is represented as a simple straight line. And that line can be vertical, can be horizontal, or can be inclined with some angle, right? But it is linear. The boundary is straight line. Once, in case of, we'll be focusing more on binary classification. So in case of binary classification, we will have only two parts, one on the left and the right of the boundary. Or it could be, there could be multiple classes that are categorized using multiple boundary lines, but yet straight line. So you have here 3 straight lines, straight line 1, straight line 2, straight line 3. So it's essentially non-binary multinomial classification. Whereas in case of, this is not right here. So look at this picture here. You see here data, you can see the blue dots are in a circular fashion. It is a pattern circle. And they can be separable using a non-linear shape, mathematical shape, which is a circle. So how do you represent a circle mathematically? Anyone? In a 2-dimensional space? No one? Okay. X squared plus y squared equals maybe r squared. Right? R is the radius. So that is a intuitive visual understanding or intuitive understanding or intuition of linear and non-linear separation and boundary lines. Essentially, these are called boundary lines. Here is the boundary line is a circle. Right? So that is what essentially this description talks about. Right? Also, the linear data is linear classifier is used when data is simple and the pattern is linearly separable. Used for the simple cases and it's fast as well. The easiest to interpret because interpretation is straightforward as you can see here. It's either this class or that class. But it cannot handle the complex data. For example, here, a straight line cannot be used to separate this circular pattern. Examples, SVM, LDA, logistic regression. Nonlinear, where the data is complex or data pattern, data has the complex pattern, like here, this circle. And the relationship obviously of the boundary line is nonlinear. So we need non-linear mathematical representation. or ready-made. Here I took a circle, but what if the boundary line is like this? How do we represent mathematically? Is it possible at all to represent mathematically this zigzag curve using one equation, or do we need multiple equations? For example, maybe this could be considered as a circle, this could be considered as a one segment of the curve, this could be considered as the other, maybe it's a combination. So data patterns are complex, hence the decision boundaries to classify the data into any class, into one class, is also complex. So obviously then it is used to model intricate patterns or complex patterns. And because of the ability to represent complex patterns using mathematical formula, certain like circle, ellipsoid, parabola, hyper, tangent, right? Readily available mathematical models exist. So it could be also easier for such certain fixed patterns for which we already have mathematical models. But for others, we may have to look at an intuitive, ingenious solution by combining multiple mathematics. Obviously, because it's complex and there is a polynomial order involved, so computationally, nonlinear classification is expensive, takes a lot of time. Time is money in computation, and it's also expensive. And of course, because of the nonlinearity and the multiple patterns, we need more data. And of course, interpretation is also challenging. It's not that easy, like here in this case, right? Where here, we know that one side is one class, the other side is the other class. But it's not that easy when it comes to this shape. So essentially, if you look at key comparative parameters of linear and nonlinear, the decision boundary there, straight line versus linear versus nonlinear. And straight line, the decision boundary is straight line in case of two-dimensional space. But if it is more than 2 dimensions, obviously it is a plane. And if it is more than 3 dimensions, then it is called hyperplane. Right? So in case of linear classifiers, the decision boundary is hyperplane. In 1 dimension, it is a dot. In 2 dimensions, I think you should have that somewhere. And we'll see that somewhere. So hyperplane is more than 2 dimensions. The performance, obviously linear is faster, non-linear is complex and expensive, right? Computational cost, more for the non-linear. Linear are faster and simple. Non-linear classifiers are obviously takes a lot of time, and they need also a lot of computational power, right? Lots of floating point operations, and obviously it's complex and expensive. Yeah, so in fact it's here. This is the representation of the linear transformation. So I use the term linear line or linear or straight line. I use the term transformation because these are all an imaginary transformation that we can plot using an imaginary space of 1 dimension, 2 dimensions, 3 dimensions, which our forefathers created a mental framework to visualize the data or anything, a fact of the life of the world, in a contained mathematical model. So as you can see here, in a 2-dimensional space, a linear transformation is nothing but which is represented using AX equals to B or Y, whatever, whether it's getting a value of Y based on X, or it's a constant value since it's a line. So one value has to be always constant. So it is a straight line, also linear transform, and represented using X equals to B or Y equals to A. Whereas in case of 3D, you can see 3D here, right? So a linearly separable data in a three-dimensional space has 3 dimensions, and it's called a plane. Right? Plane because one dimension is constant. Other 2 dimensions would vary. In this case, what is constant here? The Z, this vertical is constant, vertical axis. Whereas the 2 horizontal axes are varying. In case of non-linear visualizations, besides, but I'm just reinforcing this understanding for the intuitive understanding of this classification. If you see a data pattern like this in 2D, obviously this is one circle, this is other circle, 2 concentric circles in this case, right? But if somehow, if we can transform this data, which has 2 dimensions here, into a higher 3-dimensional space using appropriate transformation, obviously non-linear, that's 2 dimensions, 3 dimensions, non-linear, right? You can see a pattern here that you can get a hyperplane which is a linearly separable boundary to classify or separate out data pattern which is complex and non-linear into. This is also called a Kennel trick, a hack about it, and that's where the math is more important. Right? So these are all linearly separable data sets. And the representation of these boundaries, if you take 2D, x1 plus x2, a1 x1 plus a2 plus b, line, and this is a 3D plane, and it's a hyperplane, which is more than 3D and 9 dimensions. Right? A thing that has 4 dimensions, what do we call? Anyone knows? An object represented in 4D. Anyone? If you have seen the movie Thor, you should know that word. It's called tesseract. Right? All right, now let's get into a little more mathematical representation of the linear classifier. As you can see here, we have this class represented in blue shaded curved area with the decision boundary in black dotted line, and of course data in both sides. Right? One class on the one side and the other on the other side. Right? So these 2 areas that are separated by decision boundary are called half spaces. This is one half space represented or oriented towards the class A or 0 or 1. This is the other half space which contains class B. Yeah, the other one, 0 or 1. This is 0 and this is 1. Class value of class A. And of course, this line, we just talked about how do you represent this straight line or linear transformation mathematically. Nothing but A bar transpose X is less than or equals to B. So half space can be represented using this inequality. Anything less than B is one class, in this case here class A, anything less than or equals to, and anything greater than B is the other class. So this is the mathematical representation of a linear transformation, and particularly linear classes, linearly separable classes in the context of binary classification. Let us say we have two lines. We are able to identify two lines where the data points between these two lines are sparse or minimal or zero. Here we have around 3 to 4. Now, how do we represent these two lines? Simple. One has a B1 value, and the other one has a B2 value. But the transformation is still linear. And they have then the transformation when the dot product is computed, it has a constant value. So these are two parallel lines with some gap between these two parallel lines. And how do you compute, or what is the gap between these two lines? This is again assuming such data exists, right? There is nothing but it's a simple algebra. I'm not going to derive this, but you can easily derive it based on Pythagoras principle, etc. Using the perpendicular line and tan theta, etc. Right? The distance between these two lines is obviously, since these are parallel lines, this distance is constant. The d equals to modulus, because it's an absolute value of b1, b2 divided by, what is this called? Norm A. It's a level 2 norm. Also represented this way. Of vector A, which is nothing but the weights vector of the x, right? Weights vector that we would derive is provided. So the distance is between these two lines. This is important. Please pay attention because it's going to be used in the next slides. And please do this B1, the modulo or modulus of mod B1, B2, and the norm of A. That is the distance between these two lines. So intuitively, if we can separate these two classes with a maximum gap, then it is easy for us to classify the next data that we get to classify. Because the margin of error, because they are separated so apart, it's easier to call out which is what, right? Obviously, our goal is to have this gap maximum. There comes maximum margin classifier using support vector. Let's spend some time here understanding the terminology, because it is super important to you guys to understand these terminologies and concepts. It is straightforward, simple, intuitive, but you need to feel for this. You need to put yourself into a situation of appreciating and understanding these nuances. So I'm just simply re-representing what I have talked about here, right? So we have the same 2D graph, we have the same data sets, maybe color differ, angle and orientation is different, and we have two parallel lines that I talked about. I draw one extra line here. We'll talk about what are these. Now let's go one after the other. We've talked about this gap between these two lines. We call it as a margin, and we want that margin to be gap to be maximum, so that it's easier for us to classify without any ambiguity, classify any data. Hence, we want this margin, this gap to be maximum, also called this is a maximum margin area, right? This is that. Now, these two lines, right? Let me use a different color there. Right? Color we will use in this orange, right? Orange. So these two lines, they could be lines or they could be hyperplanes if it is more than 2 dimensions. So they are hyperplanes, obviously, lines in 2D. The dot if is 1D, right? They are kind of acting as a boundary, right? Because for the maximum margin, right? So they are supporting the gap. So if we can identify these supporting hyperplanes mathematically in the data set using some mathematical formula, then it is easier for us to classify when a new data point comes in. Because if we compute the value for the data point using the mathematical equation of these two lines, and if the value is less than this line, then we know that it falls this side, it belongs to this class. And if it is not only less than this, it is more than this line, that value falls in this area, then we know it belongs to the blue class. So essentially, these lines are serving as supporting, and of course, they are vectors. Hence, they are support vector lines, or they are also called support vectors, meaning let me clear it out. Any vector that lies on this line, these lines or these hyperplanes, more than 2 dimensions, they are the vectors falling on support vector line, hence they are called support vectors. So in our case here, this is support vector 1, this is support vector 2 for the blue category. This is not a support vector because it is not on the line. Whereas here, it is a support vector. Vector, what is vector? Vector is nothing but a value set with more than 1 dimension. If it is a 1 dimension, we call it a scalar. So this is the other support vector 3, because it is falling on this support vector. Right? So our goal to be able to solve this equation, when we say we solve this equation, we need the value of k bar, the weights vector, we need the value of the scalar b. Right? To solve this, we will start with the notion of we need to maximize the margin, this margin. So if we look at the mathematical representation of the margin, essentially it's assuming each is represented as here, right? A transpose x plus b is 1, let's assume 1. And A transpose x plus b here is -1. And if you just rearrange this, take the b the other side, A transpose x equals to -1 minus b, A transpose x equals to 1 minus b for these two lines. And if you compute the d based on the formula for 2 parallel lines, d is nothing but the mod of the value b, 1 minus b minus 1 minus b. So that's 2, bd gets cancelled, 2 divided by norm a. So our goal is to maximize this value collectively. So alternatively, maximizing an expression of some constant value divided by a variable a can be written as the maximizing this, as you can see here, is nothing but minimizing a, because if a is minimum, 2 by a norm is maximum. So when I say a, it's a norm a I'm referring to, right? It's a scalar value. Obviously, you can't divide something with a. It's not that easy, a vector value. It is possible though. That's where gradients, etc., come into the picture. Hessian matrices, etc. Right? So maximizing the distance essentially is maximizing the 2 by norm A, is minimizing A, nothing but minimizing the level 2 norm of vector A. And just for the convenience, we divide that by half. You will appreciate this, and some of you must have already understood by now if you have gone through Andrew's, first mathematical linear regression model. It gives the very beautiful explanation why we take 2. Half here. Any guess or anyone want to say that? Because the minimization essentially involves differential calculus, taking the derivative and equating the derivative to 0. And when you take the derivative of a second order equation, so what is the derivative of, I'm talking about full derivative, non-partial derivative, x of x squared. Anyone? What is the derivative, first derivative of x squared with respect to x? Anyone? You guys are so shy, it's 2x, right? So derivative of x raised to the n is n times x n minus 1, first derivative, right? So if we take half here, because it is a second order equation, when you take the derivative, it would be 2 into 1 by 2 norm A. So 2 gets cancelled, it becomes easier to do the equating it to 0 and deriving the values of A and B. That's the whole idea. And it does not change any hypothesis as well, right? Because you are trying to minimize, whether you minimize x or x by 2, you are still minimizing x or A, right? So SVM classifier is nothing but, right? Let's erase the whole thing. Right? Is nothing but, and this is a standard way of representing an optimization, right? We minimize this equation, also called objective function, because that is your objective. Your objective is to minimize or maximize, here in this case minimize this objective function with certain constraints that are called subject to certain constraints. What are those constraints? These are the linear transformations, 2 lines, 2 hyperplanes. One should be greater than or equals to 1 when data value 1 to m. So we said here, one side is 1 to m, the other side is m to 2m, right? Let me just now pen color. Right. So subject to, this is a class 1 support vector hyperplane representation, and this is class 2 support vector line or hyperplane, right? So this function of minimization mathematically is a convex function. You understand what the heck is convex? If you understand the convex function and visualize it, and there is a concave function as well. Many of the machine learning algorithms, the entire mathematics in a way would be very easy, and you would appreciate actually the heck of the meaning of mathematics, right? So whenever you get time, try to think deep into it, right? So this is a convex function, type of this objective function. These are constraints. These are called, non-equal, unequal constraints, because we don't have any equality here. One is greater than or equals to, other one is less than or equals to. Right? Hence, it is called a constrained optimization problem. If there are no constraints, it's just a simple optimization problem. Probably it becomes easier to solve when there are constraints. It's like this. A teacher asks, or if a parent asks the son or daughter, look, you have to get CGPA 9.5. Let's say that is one use case, one demand. or request. It's another use case or demand a request from this other son or daughter for a parent. If, hey, look, you have to get not only 9 CGPA, but every day you have to get it 5 o'clock in the morning and go to bed by 10:30, and you should have your breakfast at 8 o'clock, and before breakfast you should go do some workout by 6:37. These are all constraints, right? And whenever somebody says, okay, you have these constraints, it sounds Herculean for the second use case student or son or daughter. It's not only 9 CGPA above that I need to get, but I need to also follow this. So the point I'm trying to make jovial is that when there are constraints, it's tougher to solve, tougher to crack. When there are no constraints, probably it's easier to crack or solve, but not necessarily always that would be the case, right? So let's understand what the heck is a convex function. In a very simple, intuitive, visual way, a convex function is nothing but if you draw a function, that function is what is a function? Some value y equals to f of x bar. Right? This y could be a scalar or it could be a vector, multidimensional. But the function, this value is decided based on a function, which is a transformation. The function is it takes a value x and gives a value y, transforming x based on whatever it is, right? By multiplying in a linear way, non-linear way. So these values, if you plot them, let's take a case of only 2D. On a two-dimensional space, let's say those values are this U-shaped graph of y for various values of x, which is a two-dimensional vector. If you take any point on this function value curve, here I've taken 2 points, and if you draw a line, straight line, or hyperplane, it is multi-dimensional. If you draw a straight line between those 2 points on the curve of the function, and if that line falls above or on the function graph, then this function yielding these values using this transformation called convex. It's like your convex lens and concave lens. Convex lens is essentially, which is like a bowl, right? If you are facing it, the bottom, the lowest point is far away from it. Concave is lowest point is nearest to your eyes. That's concave is nothing but this is the concave. Right? That is called finding the maximum value. Whereas convex is finding the minimum value. Right? So a convex function is nothing but a function when you draw a line segment between 2 points on the function curve, and that line segment or hyperplane falls either on the line curve or within above the curve of the function. That is a convex function. Mathematically, it's represented for any 2 points, not for all 2 points. This is a mathematical representation of for all. We with a line is for each x1 and x2 belonging to domain D, and a lambda value, it's a closed function between 0 and 1, meaning lambda can take 0 or 1 as well. If it is an open function, it is represented with braces, which means it cannot take 0 and 1, but it can take any value between 0 and 1, not 0 and 1. But in this case, it's a closed function, closed range. It can take 0 and 1, such that function of lambda x1 and 1 minus lambda x2 is always less than or equals to lambda times fx1 plus 1 minus lambda fx. This is also linear transformation. And this is derived based on Cauchy theorem in linear algebra. Cauchy something, Cauchy, I forgot, it's a general scientist. You will learn this in mathematics. Also called triangular inequality. Right? So in a simple terms, visually, if you see here, let's take this curve where there is a breakage here. And also, even if you take a continuous line, if you take a point here, if you take a point on this curve to extreme right, if you draw a line, it is going above and then breaking somewhere it's below, somewhere it is above. That is not acceptable for convex function. It has to be either on or above, but it cannot be both. Right? And same case here. Take one here for this function, which is again a nonlinear. And this is non-convex. Because 2 points on this function curve are essentially both above and below, and they are not falling in the prescribed limits of this definition. Mathematical intuition for that is simply you won't be able to derive the minimum value for such curves. Whereas for this curve, 3D curve, or this curve, somehow you can reach, there is only one minimum, global minimum. You can reach or mathematically compute global. Whereas here, you would not know, there are too many minima here. There's one minimum, other minimum, there are many minima, as well as it is tough to compute, which is the global minimum, which is this. Right? Any questions, guys? So let's try to wrap up quickly. I hope it's not confusing so far. There are at least 10 more slides, so maybe another 10 to 15 minutes. We started late. I planned it for 1.5 hours. I promised to complete in another 15 to 20 minutes. Right? So this essentially is a mathematical standard representation of optimization or constrained optimization. This part which we went through, but this addresses a generic way. What we saw were only two inequalities, constraints, but there could be equality constraint as well, right? So an optimization problem, also called primal problem, why it's called primal, we'll get to it. So an optimum value would exist for a function minimum of fx subject to constraint. Well, exists we cannot say, but this is representation of optimization problem statement mathematically, right? Subject to two inequality constraints, one less than or equals to 0, other one greater than or equals to 0, and the third one is equals to 0. Certain constraints involving the variable x, which is the input to this function, but it has bounds or constraints. Conversely, the great Lagrange, I'm sure Lagrange, the scientist, you must have heard about his formula name, and the French or German. He has hypothesized a variant next form of this problem, constrained optimization, which he has hypothesized as a dual optimization problem to solve easily this constrained optimization problem using a function which is created based on certain multipliers, where the multipliers and the function is named after him, called Lagrangian or Lagrange function, using Lagrange multiplier. And what are these multipliers and Lagrange function? Take the objective function stated in the in here, in the primary problem. It's a primary problem. And then take each of the constraint 1, constraint 2, constraint 3, and multiply that, each of the constraint, both equal and unequal and equal constraint, using a specified multipliers, which are called Lagrangian multipliers, lambda, mu, and mu. This is mu, right? And this resultant function is Lagrangian, and that is, you are combining with the original function, multiplying each constraint, how many ever constraints you have, with a factor, which is the Lagrangian lambda I, where lambda I for gx is less than inequality, less than or equals to inequality constraint. You have to ensure lambda is greater than 0. Hx is greater than or equals to 0 constraint, for which mu should be less than or equals to 0. And the equality constraint multiplied with mu k, and there is no constraint on the mu. So you define a infinium or a minimum function, it's a minimization of Lagrange function. Now Lagrange is a function of not only x, but Lagrangian multipliers as well. You minimize that function while treating x while treating the Lagrange multipliers as fixed. So that means your variable is only x. Treat these as constants, essentially partial differentiation, treating each differentiation, treating with this as constant, this as constant, this as constant, but only this variable. That resultant function is called dual function, which is represented using pi. Pi is obviously part of, is represented using x is missing there. There should be x as well. X lambda mu is b. And now take that minimized function of pi and try to maximize. It's convoluted, but that's how it is. That's why it's very complex. Try to maximize the dual function with respect to Lagrange value, which is stated as this. Maximize subject to lambda greater than 0, mu less than 0, mu, there's no restriction of the minimization of or minimum of Lagrange. So when we solve this up maximization, this particular dual problem for maximization, when you solve, you obviously get lambda mu u, and then thereby you can derive x, a and b, not x, a and b. And that solution is called Lagrangian duality. And when you solve SVM primal problem, ax if plus b equals to less than or equals to 1 or greater than or equals to 1, when you solve for a and b using Lagrangian duality, it's called dual SVM. Right? So visually, a primal problem is essentially we have any further constraints except the original constraints. So for a convex, it is a bowl. So you are using the dual, you are trying to create an artificial function which is a replica or image of that function using the Lagrangian multipliers, and trying to find the maximum of that mirror replica, which in a way would be minimum of the final problem. That's the whole idea. It's a twisted way. Instead of solving one equation in a direct way, solving it indirectly. But not only indirectly, here there's a connectivity. If it is an exact replica, if the dual problem is exact replica, the maximum of dual problem and the minimum of the final problem will be the same. That's called strong duality. You firmly believe in either this or that. There's a duality in our spiritual philosophy as well, also called black or white, right? You say yes or no. So there is nothing in between. But if the function that you are trying to minimize cannot be exactly have represented as a exact replica, matching with it or touching with it, then even though you find the maximum of replica in mirror image, that may not be coinciding with the minimum of your original function. And there may be some gap. And this is called the weaker duality or weak duality. Duality, mirror exists using Lagrangian, but it's weak. So the maximum value you found may not be necessarily the minimum value of the primal problem. Right? Obviously, dual solving a dual sometimes could be complex, right? So when you solve using primal, it's a maximum margin classifier, straightforward. It's called primal optimization. And when you solve using dual SVM or dual problem, it's a dual SVM or dual optimization problem, dual SVM, right? Instead of solving for the AB directly, hyperplane, dual SVM obviously solves using Lagrangian multiplier. In this case, the size of the dimensions are reduced. So in a way, we are bringing down from higher dimensional feature space to lower dimensional feature space, dual space. That means it's a sort of PCA, principal component analysis, but philosophy is reduction, not exactly PCA. PCA also we try to reduce the dimensions of the features when there are hundreds and thousands, minimum tens of hundreds. Right? So I'm going to skip this. This is the derivation, minimal derivation, without obviously stating the straightforward, obvious step, right? But the key point here is the solution for dual optimization problem. These are very tough problems that are solved in the world after a long, long time after the problems have been formed, and they form the basis for many of the solutions to lots of business problems that otherwise would have not been possible. MITs of the world, Michigan Institute of Technology, Stanford, Princeton, they are well known for producing scientists, and even some of the countries in Europe, who have not only formulated such formulations for real world problems and solved them, because of which we are today what we are. Otherwise, we probably could have been living centuries behind. Right? So anyway, the key piece here is when you solve whether using primal or dual, using the primal or dual optimization problem, it is easier for you to get one of the two classes because you're finding A bar, weight vector, and then the B by weight classes, by linear separation. But real world is not linear. You see, obviously, in our project, it has not been linear in terms of the data pattern. So, how can we achieve a linear separation somehow for a data that has non-linearity pattern? And that is not possible to separate linearly, which is nothing but a real world problem. How is it possible? Right? Let's try to spend a couple of minutes here to understand what we mean by non-linearity, classification and determinism. So we started obviously skimmed through the dual problem. So if you look at the dual problem, this particular problem, the solution is nothing but it is the dot product of two data points. The transpose of one and the other data point, also called inner product or dot product, which is mathematically represented using this. So bigger angular brackets in between x and x3. So a nonlinear data set in its higher dimension called C or C at psi Greek alphabet, it might become linearly separable if transformed into higher dimensional space. So let's take an example here. There is a data pattern which appear to be in a concentric circle in 2D. If using this essentially, this equation or transformation, nonlinear transformation, because you have more than one order, right? You can try this, MATLAB, etc. You can easily visualize this. Becomes in 3D this form. It's like a sphere, but the blue and red data points can be visually and intuitively seen being separable using a linear hypercube. So the key challenge then for us, how to find such function that translates the lower dimensional data into higher dimensional linearly separable data, yet without calculating the entire data space. Because here it's only a dot product, all we need in this formula of dual problem or dual optimization. And that is essentially the kernel trick. So we are taking notion of central or kernel or key notion of transforming the lower dimensional data into higher dimensional data to compute a dot product without computing the entire data space point. It will be computationally expensive, yeah, and probably impossible if it is millions of data. All we need is we are using an equation to compute the dot product without computing the entire data points for each entire higher dimensional data points for the lower dimensional, each of the lower dimensional data. That is a trick that uses a function, a kernel function. A kernel trick comes from the kernel function. The kernel function is essentially the one that has a form that can be used to derive the dot product of two. That is a kernel trick. SVM with a kernel trick is called a dual SVM or kernel SVM, but non-linear data. Dual, even if linear also, you can call it dual SVM using the dual optimization, but when you are using it for non-linear separability, non-linear data separability, and transforming into higher dimension, making use of a kernel function, then it's called a kernel trick, SVM with kernel trick, right? So I was talking about four-dimensional output. It's a test of that. So kernel function, there are multiple kernel functions. A linear kernel function, straightforward. It's a linear kernel function, it's linear in higher dimensions, isoplane. Polynomial, so some curve, right? Then radial basis, something similar to a Gaussian, standard normal distribution, standard distribution. And exponential Gaussian, so changes exponentially. So in the project, I have requested you guys to use linear kernel and, if possible, RDF or Gaussian kernel model. These are already available in the SEC of Python, scikit, right? So how to choose? It's on the complexity of the data. How to choose the kernel function? So you have to do or have some sort of visual exploration of the data, and then choose a particular nonlinear function or kernel function. These are the visual representation of decision boundaries for linear, kind of linear straightforward. So if you see here, this is the separation, which is non-linear and it's more like a bell-shaped stuff. Polynomial curve. And yeah, the other one is sigmoid like S, right? Just for you to get some idea. So simple, the value computed based on this sign of the solution from the dual optimization. If it is positive or negative, based on the positive one class in that boundary. If it is negative, the other class. So I'd like to draw your attention of two contradicting or conversely, intuitively converse functions, which we have seen in the PCA. PCA reduces the dimensionality, whereas the kernel increases the dimensionality, right? Increases implicitly. In PCA, we are computing the principal components. They are less. But in kernel tricks, we are not computing. We are merely using a mathematical formula that gives the dot product in the higher dimensional space without explicitly computing the entire higher dimensional data points for any given input lower dimensional data space. Right? Essentially, for the nonlinear transformation, the kernel trick, whereas PCA is to reduce the complexity, and it's a linear. PCA is a linear transformation for reducing it. Whereas increasing the dimensions, we are transforming nonlinear. PCA is simplifying the process of computation. Kernel trick is actually, it is creating a richer separation between otherwise not possible to separate linearly. PCA is essentially approximating the separation, as you can see. You can see PCA is bringing, it's like your Microsoft Kinect game. You can see only skeletons, right? The infrared, essentially, they are using the PCA to reduce only to core minimal 2 dimensions, even though you have 3-dimensional data plus hands protruding, coming out, etc. If you see the Kinect scanning, right? Then we create any Kinect game. Also, that movie, Mission Impossible movie, high spin Morocco controls. Whereas in the kernel trick, you are increasing from 2D to 3D to have a separation, linear separation. Right? All right, I promised 20 minutes, but another 5-10 minutes. Also, there's one often that you hear topic that I would like to draw your attention. There is in algebra a kernel that you must have heard, particularly when you had dealt with your mathematics, matrices mathematics class, where you computed null spaces, left null space, right null space. Null space also is called kernel in algebra. So null space, so this is the matrix is a transformation. We are essentially transforming something in one dimension or multiple dimensions to the other dimension, more or less. So if you take, it's nothing but a linear transformation. So from one space B to the other space W, essentially linear, to the kernel end or null space is nothing but all those points in your original space before transformation, which are transformed to a single point in the new null space. That is what X is. LV equals to 0, actually origin, the 0 value. This is the inverse function. So that means the value in the transformed space for which all those points that have the value 0 in the transformed space, but fall in a certain region. Obviously, this is finite if it exists. And that is called the kernel in the original space. And this is essentially a matrix transformation, linear matrix. It's very, very important for you guys to have a clarity on the topics and notions and concepts. So it's not that easy. but you have to keep studying and understanding these topics multiple times. From this kernel comes a famous rank nullity theorem. Rank is essentially critically important in deriving a lot of mathematical machine learning models. Right? Then each machine learning model uses the matrix transformations and multiplications for deriving the optimization. So if you look at here, the dimension of V, this is V. V dimension is this. This can be summarized or mathematically composes or constitutes of all these points that transforms to this single value plus rest of the transformed space. So, image L is nothing but this, and image L, this entire area plus this point plus the dimension of this point in the original space, which is this kernel dimension of kernel. E is the total dimension of image L. This is called rank nullity theorem. And this is just a sidebar topic. It's super interesting if you guys really get into the kernel and mathematical problems. I'm going to skip this. Probably we'll spend slack variables tomorrow. What are the slack variables? How are they related to SQL? And what is the mathematical optimization? We spend some time tomorrow. Accuracy and efficiency. So there are 5 to 6 parameters. We all know this. Accuracy. How do we compute accuracy? We spend some time tomorrow. Precision, recall versus reference score, confusion metrics, ROC curve, and future important. I'm asking you to compute all of these for the project. Plot that. Drag to the key takeaways. Simple. SVM is a powerful classification. Works also well in the higher dimensional space. Also for non-dimensional, non-linearly separable data with analytics. So this is effective when you use hyperparameter data that is invalid. You get invalid data and so on. And what did we say? Visualization, etc. That is applied in the previous slide. Yeah. So project overview. This is to diagnose breast cancer. So cancer is more of a colloquial term, but clinically they are tumors. And cancer is caused by malignant tumor. Tumor is nothing but lump. Take that lump. All lumps are not cancers or malignant. There could be lumps. Human body could create lumps. But if it keeps on growing, then it is malignant without any arrest of the growth. The benign lumps are, they don't grow and they are benign, harmless. So diagnosing breast cancer based on the diagnostic date, which is described using numeric values, 150 or 100 parameters. This data set is available readily in the scikit, and I've also given descriptions today. So let's first understand the objective. So we should implement an SVM, preferably linear as well as RBF, to classify the given data sample, whether it has malignant tumor or it is a benign tumor, or whether it's cancer causing, or whether the person has the cancer or does not have the breast cancer. We're talking about only breast cancer. This is not common for all cancers. Data has to be loaded. It's part of the SQL, like I said, it's a standard set. University of Wisconsin, and see the links here as well. This was actually published, I don't know, 20, 30 years back in a paper. I've given the link here, all the links here to those researchers and professors like that. So it has around 570 samples representing each representing a patient with set of feature values. You should use this data for training as well as for prediction, meaning you have to divide 80-20 or whatever is the appropriate. Okay. Hyper parameter you have to choose, usually 20%, right? For validation and 80% is super. So use the SAM or linear RBF for the classification. You have to load it from the scikit, train it, and predict, and plot all those parameters. Accuracy, precision. So I think the data is good here. Data source and publishing the papers published on it. And then where we can download this data if you want. But otherwise, you can just load it from scikit. It load data with I think I'm subduing in the shell code, or you can do ChatGPT and use it. Let's look at the demo. Okay. I hope you guys can see my screen. Okay. So loading representing the placeholder comments. So there is load breast cancer and data sets. And fill the description of the data using this predefined attribute of data frame loaded or data frames loaded. In all that I'm not going to go through. We'll spend more time tomorrow. So I've used some T-distributed stochastic neighbor embedding just to see the data pattern in the reduced dimension. So this is sort of CCA, but for visualization. It has reduced the dimensions of input data on this side into only 2 dimensions. So you can see red are causing malignant means green or the image. And this is for the standardized data. You know, mean 1 and mean 0 and variance 1. Next, this is just plotting it. You will spend some time on parallel coordinate plots. You will spend some time. Yeah, so here train and predict and then plot all the parameters. Yeah. The confusing matrix, ROC curve, then the precision recall curve, feature importance, and the F1 score. All these parameters you already know. And accuracy score as a curve based on the decision threshold. I've used multiple here, multiple models, RBF, then polyclonal, sigmoid, logistic regression, just for the heck of comparing what is the accuracy. If you see here, this is the comparative accuracy. It would be great if you guys can do this as well. Obviously, it doesn't matter for us, both linear and RBF, non-linear classifiers are giving the same accuracy, but better than any other linear or sigmoid kernel or even the linear regression, or even k-nearest or manual gains or random parts. And then plot the accuracies, comparative accuracies separately for each model. You can do just for these two, linear and RBF. You will have to get to for the rest. And this is the IST curve, F1 score, and then the decision boundary. You can see pretty much linear. whereas the RBF tries to get as non-linear curved decision body. Probably better, but in our case, the accuracy is not showing any improvement, even though we have a non-linear decision. And this is for the rest of the model. Good, great. If not, it's a. And then create a PDF out of it, right? PDF. So you see the PDF. Now you can see we can create a PDF. And let's also see the shell code. I think shell code is in the dimension. The imports are given, and I have also given a method to you guys to add the watermark. Loading of the data also I've given in the code, printing the description of the data. And then I've given the comments what you guys need to do. Any certain code lines I've already given. If not, obviously I know you guys are going to be execute your cloud. Any questions, guys? Couple of minutes for any questions. Is anybody else? All right. Looks like you guys have already left. Thank you. Bye bye.